to start?
Yes, you are.
All right, sounds good. All right, so welcome everybody to today's session of REYES. I'm really excited about this session. This is going to be a talk by Professor Olivier Pfister, who is, I've gotten to know him. So he's a professor at University of Virginia, and I've had the pleasure to get to know him because we have a joint grant exploring ideas of quantum computing, connecting the kinds of physics that he's going to talk about with nuclear physics, which is what we do at Jefferson Lab. And so we decided to join forces and we got a big grant. And so we've been working side by side this past year. I've learned quite a bit from him. He's a great speaker, and I think a lot of you will enjoy him. So for a little bit of background, he got his bachelor's from the University of Nice, which is where he's at right now, physically in this moment. He got his master's and Ph.D. from the Université Paris-Nord in France, and then he moved to the US and did a couple postdocs, including one with John Hall, who got a Nobel Prize in physics. And since then he's become faculty at University of Virginia, doing the kinds of work that he's doing right now. He's also a fellow in the American Physical Society and a member of the Optical Society of America. So it's just a real pleasure to have Olivier here with us. So please take it away, Olivier.
Thank you very much, Raul. I appreciate. I would like to, I don't know if people can interrupt during the talk, but if they can, they should. I don't take interruption as a mark of disrespect. I take interruption as a mark of interest. So that flatters me rather than annoys me. So please, if there's something then there will be things that are not clear. I'm not that good a speaker. But contrary to what Raul said, I try hard. So I'm going to try to tell you about light and quantum computing today, and trying to really also tell you about what we call the second quantum revolution. It's this part of things that we're working with Raul, trying to understand how we can use quantum computers to calculate things in nuclear physics, for example, that would be useful for Jefferson Lab or the EIC. So this is research. So I'm not a nuclear physicist. I'm a quantum optician. I'm an atomic molecular optical physicist. I do a lot of stuff with lasers, and I shine them at atoms and molecules, do spectroscopy, and I also do quantum optics. So I'm going to show you my group. Actually, there's some people who have left. Raj graduated, went to Caltech as a postdoc. Carlos is a postdoc here. He's a theorist. He works also with Raul. Raf was a theory postdoc. We're an experimental group, so it's funny. We have theory postdocs, but it's very, very useful to have theorists to tell us what to do. He went with Carl Caves at University of New Mexico, and then now he's in Australia at RMIT University in Melbourne. Awin was with us. He's an experimentalist postdoc. He was an experimentalist, now he's at University of Oklahoma. And we have Chen Hung, Xuan, and Miller, who are the graduate students at the time. And we have new graduate students joining that I haven't put on that picture. I need to update. We have collaborations with a lot of people. We have collaborations between different countries, Israel, Brazil. We have collaborations with people who do different things like engineering, electrical engineering, NIST metrology, photonics. These are the colleagues in France I'm working with. And a lot of theorists here in quantum optics, quantum information, condensed matter physics, nuclear physics, Robert Edwards, some of you know him. He's the head guy on our collaboration with Raul. So let me tell you about what we call the second quantum revolution, which is really the kind of there's a lot of buzz about quantum these days, and there's a lot of hype, and there's a lot of overhype, and there's also some excitement that's legitimate. And so second quantum revolution, does that mean there was a first one? Yes, there was a first one. The first one was when quantum mechanics was finalized, and that was in 1927. And that's when all the pieces were put together. In particular, the fact that waves and particles, which are two different concepts, I'll come back to that. Two different concepts in classical physics are actually working together in quantum physics. And quantum physics has also been amazingly successful at explaining everything but gravitation. So gravitation is different. Gravitation is not quantum. Gravitation does not work with quantum. I mean, it's hard to make work with quantum, and it's hard to test because it's such a weak force that you need, planets, stars, and black holes to see it. And there's also the problem of dark matter and dark energy, but okay, this is one thing at a time. The first quantum revolution was that of technology that was enabled by understanding of quantum physics. And so 3 examples: transistor, the laser, and magnetic resonance imaging, which is kind of cool. This is an image of a heart, and I found that on Wikipedia. I think that heart is actually, there's a pathology here. There's way too many blood vessels there. So how did that come about? Well, look at the first row here, the first quantum revolution. And the big discoveries that enabled them were discovery of a photon, which is the particle of light. And light is an electromagnetic wave, but it's also made of particles. And that was Einstein in 1905. Stimulated emission, Einstein 1917. Though both those concepts led later to the invention of the laser by Sherlock Townes, Myman. In 1961, the first laser, there was the maser and then the optical laser. The understanding of electrons in semiconductors, so really, the understanding of matter at the quantum scale, and these are all Nobel Prizes, Einstein, Bloch, Peierls, Schottky, gave the transistor, so the current amplifier that we know as a transistor, another Nobel Prize here, Nobel Prize for the laser as well. The understanding of a spin gave nuclear magnetic resonance and magnetic resonance imaging. And so the second quantum revolution, so this is, those inventions, laser, transistor, NMR, MRI, have really revolutionized our society. I mean, they've changed technology, they're still changing it. It's still happening. All the uses that the laser, for example, has been put to, from surgery to, communications with optical fiber internet, right, and fast long haul and fast rate, high rate telecom, GPS, and so forth. Now, the second quantum revolution is that of more quantum discoveries, but this time the technology is coming, but it's not there yet, but some of it is coming, it's there. The technology is going to be quantum. So I'm not going to give you a lecture on quantum mechanics, but I'm just going to give you some examples, right? So that you see a little bit what it is. And so there was things as squeeze noise interferometry discovered by Carl Caves, which is now used in LIGO, the Laser Interferometer Gravitational Wave Observatory. I will show you a few slides about that. So it's a quantum sensor, and it's better because of quantum states of light. So because of quantum optics, because of the quantum nature of light, because of, we care about what the photons do, not just what the electromagnetic wave does, which also is the nature of light. Quantum key distribution gave quantum communication, which is things that are happening right now. And then there's the ideas of quantum simulation and quantum computing. That's an example of a quantum algorithm, the factoring algorithm by Shor. Which are giving those examples of quantum technologies that are still a ways away, but we're working hard. This is the research I'm doing. We're trying to make that happen. We're trying to make that a reality. So understanding quantum, how is that possible? Well, understanding quantum means that you have to understand the wave-particle so-called duality. It's not a good word, and I will tell you why in a second. But Niels Bohr, one of the founding fathers of quantum physics, at some point had to design a coat of arms because he was to be knighted by the king of Denmark. And so he had to come up with, and so he designed it himself, and he chose the Tao symbol of yin yang, and the contraries are complementaries. And so he had this idea, and it's all, what is this idea of yin and yang? For Bohr, it's wave nature and particle nature in physics. So for him, it was super important to illustrate that, and that's how it resonated with him, with that Tao symbol. And it's important because it's not intuitive how to understand this, and sort of how to think about quantum is difficult because, so for example, here, this is a very simple example where, the girl here looks at this cylinder from the side and she sees a disk. And you could say, well, that's the wave nature of things. And the guy looks down on that cylinder and sees like a big rectangle, right? So these are two different objects, but these are just two views of something that's more complicated. In a sense, this is kind of like, it's a funnier way of displaying it. Along with that famous Feynman quote, I think I can safely say that nobody understands quantum mechanics, which is fine. So you have this, you can imagine that one end of this object is the particle nature of things and one end is the wave nature. And it's not just about understanding the wave and the particle, and it's about understanding what's in the middle. So of course, this is a joke. It's just designed to make sure you're watching the screen and, my eyes hurt. But can we understand this as a whole? Can we understand this object as a whole? Can we have an intuition? Can we have a physical intuition? And beyond that, can we build on that physical intuition and understanding to do quantum engineering, right? What is quantum technology? Well, we can do classical engineering very, very, very well. I mean, engineering is completely awesome. So I always say the scientists discover, the engineers invent, and it's either one is hard. It's a full-time job. It requires creativity, intelligence, ability to solve difficult problems, and making discoveries and making inventions. Can we make quantum inventions? Well, it kind of requires understanding how quantum works, right? And so this is just a way for me to illustrate, but it's not just a cartoon. It's actually difficult to really convey that, to really understand it. The way we physicists understand quantum is by learning it 3 times, basically. Like you're undergrad, then you're a graduate student, and then you relearn it when you teach it, and that about does it. And by then you're about okay with what it means, but it doesn't mean we really understand the whole picture, but at least we can use it correctly, at least in my case. So now I'm going to tell you about waves and particles. So before I do that, I'm going to go back to this. I'm going to show you a little demo. So you can go to the University of Colorado PhET website, PhET. They have lots of demonstrations. You might have seen those before. It's very, very awesome. I use it to teach all the time. And so I'm going to show you waves. So that's the stuff that we're all very familiar. This is like the sink. It's full of water, and I'm letting the faucet drip, right? And I'm getting those nice little waves, and we can image them like that as a sine wave, right? An ondulation in space that propagates in time. Okay, fine. So nothing new there. Now I'm going to turn on the other faucet. There we go. And now I'm going to have 2 waves that propagate. But you see that when they propagate, they do things that particles don't do. Particles don't interpenetrate each other, right? They pull, and when you play pool, billiard balls, they collide and they affect each other. Here, waves can interpenetrate, go through each other, and by doing so, they add where they overlap, and that's called interference, right? And interference is interesting because, well, if 2 waves are in phase, I don't know if I can do a graph with this. It doesn't really do anything for us. But if two waves are overlapping in place where they're in phase, well, it means that the circles from one, so the blue circles are like the crests of the wave, and the black circles are the troughs, right? And so when you have a place where the two crests are overlapping and the troughs are overlapping, like here, you've got interference. The two waves add up in phase and make twice as big a wave if those two waves are identical, right? And that's constructive interference. And then, of course, if you're here, you see this is an interesting place where it's all gray in between the real bright crest and the black trough, right? This gray is exactly halfway. Well, because whenever you have a crest for one wave, you have a trough for the other one. So when they add up, they're just like give you an amplitude in the middle, and vice versa, trough for one wave, crest for the other one. And then when they're both, and they're always exactly out of phase, 180 degrees out of phase. So here you have destructive interference. Right? And if you're bobbing at the surface of the water, as Raoul said, I mean, Nice, I'm enjoying the Mediterranean Sea a lot. I was born there, so that's my hometown. And I'm working with some colleagues there very seriously, but I can go to the sea and swim. There's not a lot of waves on the Mediterranean, but sometimes you can bob and it goes up and down and you follow the crest and troughs, right? But here, if you're on this line here of destructive interference, there is no bobbing. Well, you're not going up and down. There's no waves. The water is perfectly still. It would be a really, really useful thing in a storm if you had destructive interference like that. But you need exactly two waves, like equal amplitude, and exactly to be at the right place where the phases are opposite. Okay. So this is standard stuff, right? This is not super new to a lot of you, but I like to really go back to simple concepts. So then you can do waves with sound. So here we have this animation. This is funny, which is exactly the same thing, but it's just like loudspeakers. But you can get destructive interference, and if you've been in one of my lectures or in any introductory physics class, they have demos where sometimes if you put yourself somewhere and you have the right amplitude of sound with two loudspeakers, you can actually negate the sound. That's how actually noise canceling headphones work, right? They have a mic that captures the ambient sound from outside and superimposes it inside your ears with the exact opposite phase. So the noise is a superposition of lots of different waves, lots of different frequencies, and each of these waves is just shifted by pi with the right amplitude, the same amplitude, so that it destructively interferes and you get nice silence inside your headphones, except for the music and everything you want to hear that is sent through a separate channel. Right, so destructive interference is super useful. So now we're going to do the same thing with light, and it's like, okay. So light is a little bit different, right? Because light doesn't propagate that slow. It propagates at the speed of light, right? So it's not like air or water. Actually, people say, what does light propagate into it? It actually can propagate in vacuum. So people were trying to understand that. There was the hypothesis of the ether, and no, there's no ether. It's just electromagnetic waves, but they do the same stuff, right? So except we can't see that. Like, it's very easy to fill the bathtub and poke the water with fingers and do this experiment. It's very, very easy. But with light, you can't do that. But you can still do interference, and you can, for example, have a laser go through two holes or two lasers and have them interfere. And the best way to see that is now this light is an electromagnetic wave, which means there's something called the electromagnetic field, and I'm not going to go into the math for this, but the field oscillates, right? It oscillates up and down very, very fast, 10 to the 15 times a second. So we can't really see those oscillations like we see like bright and dark and bright and dark. But when there's an interference, if it oscillates constructively, there's light is bright. If it is destructively interfering here, like the water is not oscillating, then this is when light is going to be dark. So I'm going to put a screen there so that you can do an experiment like that with two lasers, and you're going to see what we call interference fringes, right? So it's going to be bright and dark and bright and dark and bright and so on. So that's exactly the same interference as what you have with water, as what you have with air, vibrating air sound. It's the same thing, it's wave stuff, right? No difference. All waves, they interfere. Now, we're going to do some quantum. Because light is also made of photons. So photons are particles that have no mass. Light is completely ethereal in that sense. It's a bad word for that. It doesn't have any mass, it's not matter, right? But they're grains of energy for a particular frequency. Those grains have a particular energy that's related by Planck's constant. And light, if you were able to dim the room light all the way down to, you know, the smallest possible energy would be 1 photon at a time, no less than 1 photon. That's why it's called quantum. It's quantity. There's a finite quantity for some physical quantity that are quantized, and they have indivisible units. So for example, light, it's the photon. Okay, so now I'm going to have those photons, and those photons are they're like particles. So if I send light photon by photon here, you know, I have a particle coming out. I don't see where the wave is. Right? And so this is actually getting a little bit complicated. Like, how do we think of these particles? And light is a wave, but now we're sending light with such a low power that it's just one particle at a time. Here, there's great many photons. There's a lot of photons. There's like too many to count per second. But if we send them one by one, we can see them hit the screen, and we're going to see a little spot of light here or there or, you know, anywhere. And so we don't see where the wave is. And I'm going to show you now an experiment, which is a real experiment. It's not a simulation like that, although these are also real experiments that are easy to do. But it's easier for me to show you little cartoons. I'm going to show you now a real experiment. So I'm going to go back to the slides to show you what it looks like first. Okay. This is somebody who did, good colleague of mine, Jean-François Roch, from École Normale Supérieure de Cachan near Paris, did that experiment in his lab. He had a source of light. It was not a laser, it was a special source. It's called a artificial atom that can emit photons one by one. And so he had the light emitted such that it could emit first light at high power. So he'd send the light, and it would flood over this wall here that has two little holes. And that makes exactly the same experiment as I showed you before. It's like the same as two lasers that are emitting, you know, waves from point sources. So it's the electromagnetic wave is like what we call a spherical wave. And then you get interference. So that is kind of like a detector that's moved around, and this is the fringes, you know, bright, dark, like I showed you before, okay? So, fine. So that's the wave nature, exactly what I was showing you before. But now he's gonna turn off the high brightness of his source so that it really can emit 1 photon at a time. And here things are gonna be interesting, because the photon can go, and it goes through that hole. Right? And I told you, photons are indivisible. They're quanta. They are like elementary units of light, elementary particles. They're elementary particles. The only elementary particles I work with, but they are. And therefore cannot be split, right? So the photon will either go here or will go there. It won't go through both. And you can make sure of that because you can put a detector here and a detector there, and you can count how many photons there are and whether you have photons in coincidence. And if you send photons one by one, you will never have a signal from both detectors at the same time. The photon will go either here or will go there, right? So it's a particle. No ifs and buts, it's a particle. It does particle stuff. It doesn't divide. It goes here, then it's not there, or it's there, it's not here, right? Okay. But at the same time, we know that when there's plenty of photons, and we don't care about the photons, we just let plenty of light, we get interference fringes. And what are interference fringes? Interference fringes are resulting from a superposition of a light that went through this hole to the screen and the light that went through that hole to the screen. And because, depending on where you are on the screen, the path from this hole to the screen and the path from that hole to the screen are different, and therefore the two waves can get phase shifted and could get, you know, in phase or out of phase, depending on what the phase shift, the path difference is, right? But now we're sending photons, but it's the same source. It's the same physics, right? So what's going to happen? Well, I'm going to show you. Again, if you want to interject, please don't be shy. All right. I'm going to show you the movie. So what I'm going to show you is this screen here, right? When they send the light photon by photon. So here you go, that's the screen here, okay, that black rectangle. And it's gonna go fast at first. You're gonna see little dots arriving, orange dots, when I start the movie. And they're gonna count, they're gonna tally the dots like along vertical columns on the screen at the bottom of the screen there. Okay, and ready? Let's go. It goes photon by photon, and you see they arrive all over the place. Each dot is a photon. This incredibly sophisticated array of detectors. Right? Each dot is a photon from the source that went through one. It's actually slits, not holes, vertical slits. But then, as this goes, something interesting is happening, right? So you see the counts of photons. Here, there are a lot of photons, and that's a lot of counts on the peak here as well, here as well. But here in the middle, there's practically zero photons. It's dark, right? There's very, very few. There's a few because the experiment is not perfect. They should be exactly zero. It's pretty close. And you see that, in fact, what we're getting, you remember what we were getting when we were looking at the cartoon, the University of Colorado's PhET simulation, right? There was interference fringes, and this is what happens. The interference fringes are coming back. There are places where the photons never go. Even though we send the light particle by particle, the wave behavior still applies. And if you've heard of the wave function for atoms, well, the field interference of the electromagnetic wave plays the role actually of the wave function for the photons. This is how quantum physics work for light. Now, that's pretty cool, right? That was personally, as when I was a student, it was kind of a marvel for me. When I was an undergrad, I was like, ooh, I'm doing this shit for the rest of my life. And that's what I did. What can I say? So waves and particles, photon by photon. Hey, how about electron by electron? Well, in Japan in 1982, they did a very nice experiment. They had a source of electrons, a cathode, right? And emits electrons. This rod here is metallic rod. These two plates are negatively charged, which means they repel electrons, which are negatively charged as well. And therefore, each electron, because this source can emit electrons one by one. So electrons are very, very, very well-defined particles. They have charge, they have mass, you know, we cannot miss them. It's not like evanescent or anything. It's very, very real particles, right? There's no mistaking the fact that they are particles. They're a little chunk of matter. But they are elementary particles. They are quantum particles. They are quantum objects. And so now we're going to give them the possibility of going, you know, this cartoon of the skier goes down the slope and he sees a tree, and then he sees the tracks of somebody who went, you know, directly at the tree, and then the two tracks of each ski go around the tree and keep going. I should have put that cartoon in. And then the guy scratches his head. What happened here? Well, we're going to do that with the electron, but it's only one electron. It can go this way. And then there's a detector that has high sensitivity that can see, like the screen before, it can see single photons, one by one. Here the detector can see single electrons. And we are going to look at what happens, you know, as the electrons strike the detector plate, which is a two-dimensional detector, and see what happens. So there's a movie, and that's this movie. So you're not hearing the sound. The guy is actually narrating the what's written on the screen. But each of these dots is an electron. So you see that it's very, very, very slow. You notice that they're zooming out a little bit because they cheated. They zoomed in a little bit. And then I spare you all the thing. Is exactly what we talked about, right? So it looks like the electrons are coming at random all over the place, right? But then if you zoom out, and they're going to speed up the movie, they zoom out, see that they zoom out a lot, and they speed up the movie because it takes 30 minutes. And at the end of the day, there we go. There you go. So at the end, you see that clearly here, there's a lot of electrons that hit here and here, but here there's practically no electrons, So if you have this it's called the Young's experiment, the double slit experiment, you can do that for electrons as well. The wave-particle duality that I was talking about, it's very real in quantum systems. It's very, very present. It's happening for anything. It's happening for particles of matter, particles of light. It doesn't matter. It doesn't light. Okay, no, it doesn't work. It's a feature, an essential feature of quantum mechanics. And so we have to understand that feature if we want to do quantum technology, if we want to come up with quantum technology that's going to be useful in the second quantum revolution. And so that's what I do. So now I'm going to give you examples of stuff that uses the wave-particle duality because it's quantum technology. So here's one of these, that's the most advanced probably sensor in the universe, is LIGO, the Laser Interferometer Gravitational Wave Observatory. So what is this? Well, it's a microsonic interferometer. So I have this kind of like thing here. There's a laser in that building here, and there's a laser beam. You know, it's going to go hit a mirror that reflects half the light and transmit half the light. And the two beams are going to then travel down 4 kilometers of vacuum tube. They removed all the air, because even though air is transparent and, well, there's still some tiny effects that will disrupt the measurement of a gravitational wave. More about a gravitational wave in a second. But after the 4 kilometer vacuum tube, there's suspended mirrors here and one there. So those suspended mirrors can move, you know, if there's something perturbing them. And their masses are also as heavy as they can make them. They're 40 kilogram masses. Then the two beams go out, bounce, come back. When they come back from the mirrors here, you have two waves that superimpose, that overlap, therefore they're gonna interfere. right? And the result of that interference is going to be seen on the detector here, right? And that depends on whether the path here and the path there were different or not. If they are exactly the same, then two waves will come back in phase, and therefore you will have bright light because it's constructive interference, and the waves oscillate in unison. If this path is different by half a wavelength of light, then the phase is changed by pi radians, or 180 degrees, and then the light will have destructive interference, so it will be dark fringe on the interferometer. So that interferometer can measure very precisely the path difference down to the wavelength of light, which in this case is 1 micrometer. So it's actually a fraction of the wavelength. It's actually a tiny fraction of a wavelength because they can measure the difference between the distances down to 1,000th of the radius of a nucleus of an atom, which is 1 femtometer, 10 to the negative 15 meters, 1,000th of that, which is 10 to the negative 18 meters. It's just unbelievable, but it's true. And so if the mirrors here move by that much, they can tell. And why would they move? Well, they could move because, well, somebody has been shaking the ground or something has been shaking the ground, which is a bummer because that's not what we want to detect. But there are several gravitational wave interferometers. There's two in the US, one in the state of Washington, which is the one represented here on the photo. There's another one in Louisiana, in the middle of a forest, so it's very different environment. There's another one that's working at the same time in Italy, and there's one in Japan in the middle of a mountain. They dug into a mountain to install it, and I think it's turning on now. When all these interferometers see something at the same time, then you say, oh, this is coming from out there, not just, you know, an earthquake near Washington State, no, or Italy or something. No, it's like so many different places over the planet. If it happens, it's something. And what is it? Well, when two stars collide into each other, you know, the supernova happens, something big in the cosmos, two black holes, you know, collapse into each other, crunch, coalesce, and make a bigger black hole. There is something about space-time that was put into words as space-time tells matter how to move, because that's how you write the equation of motion of any mass that moves, space-time. You tell where the position is at each time, and you write a trajectory. But at the same time, that's general relativity, that's Einstein's discovery. Matter curves space-time. Mass tells how space-time how to curve, space how to curve. And when space curves, and for example, you have two black holes that orbit, a black hole binary, each other, right? The curvature of space-time is changing because the two black holes are moving, and there's two of them, and it sends ripples out there that propagates, and these are gravitational waves. Space-time moves. So like, what does that mean, space moves? It means like I'm shrinking and expanding, you know, because the width of my body is changing. The physical width, I'm not changing, right? It's just space that changes. It's extraordinary to think about. Okay, it changes by 1,000th of a radius of a nucleus of an atom, of all the atoms that make me. So I'm not going to be able to tell. It's not going to do anything to me. Not going to do anything to my cells, to my health. I'm not going to be able to notice. It's too small. But LIGO can. LIGO can notice. And the signal is light interference, like I told you. It's a Michelson interferometer. But the noise background is the photon count statistics, and that is something that we can do if we care about the photons. We can actually lower the noise floor of the detector and making it more sensitive to tiny signals, because now they're used to be buried in noise, but if you have less noise, then the tiny signal sticks out of the noise and you can see it. And so that's how LIGO can see things. And it's a quantum sensor. So this is again the interferometer. It's a more complicated thing, but you have a laser. Let's ignore those things, those recycling mirrors and those cavity mirrors. These are the two sensing mirrors at the end of a Michelson. So the laser comes here, splits here and there, comes back, recombines, make interference, right? But the splitting is actually dictated, well, each photon of a laser can go this way or can go that way. Each photon is gonna choose. It's exactly like what? The photon that hits the two slits, it can go through one or it can go through another, right? And how does it happen? Random, we don't know. God playing dice with the universe. Einstein didn't like that, but that's the best explanation we have for it. And so this is the same thing that happens here. It goes this way, it goes that way at random. And that actually gives these photon statistics, those grains of light, the way they distribute themselves, give the detection noise of the interferometer as they split here. But when they split here, they interfere with a field of light that we could send into that guy. And that field of light is generated by another laser. It's a very, very weak laser, but it's a very, very clever laser because it's a laser that emits photons. So I'm gonna skip all the details there. It just, remember, it's a laser that emits photons 2 at a time. That's all. But when you do that, you're sending. Now it's more complicated because this guy interferes, the regular laser of interferometer interferes with very, 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 very weak quantum optical field, but that's emitted 2 photons at a time. And when you do that just right, that you have to control a lot of things, then it gives you a modification of the detection noise for LIGO. You remember those photons, how they split? That gives you the, I'm not giving you the detail, but that's giving you the detection noise floor of the interferometer. Well, now if you have this 2 photon laser, optical parametric oscillator, and remember that because we're gonna see it again in a second in my trying to build a quantum computer. And boom, they did it. This is in black. This is a noise curve of the interferometer versus detection frequency. It doesn't matter, it's not important, but in green is the noise detection. There's some peaks there that don't change much, but the noise floor that you see is lower, right? That's when you use quantum light. It's when you use the 2 photon sources to change the photon statistics. And that doesn't change the signal, which is the interference of waves, but it changes the noise, which is the way the photons distribute themselves between the atoms. Okay, so yes,
Olivier, I'm just going to tell you, you're at 2:45. So maybe let's say, do you have? I'll give you 5 more minutes. How about that? And then we can see if there's any questions. If not, I'll ask you some questions.
Okay, I'm going to so. There's other, like this is Chinese satellites that send photon pairs between interferometers to establish quantum key distribution applications. And I'm gonna just, because I don't have too much time, but I want just to show you very quickly how the quantum computing works for us. So a quantum computer, I'm going to go very, very fast because I took a lot of time explaining the wave-particle duality. But the quantum computer is made of bits, quantum bits, like qubits, and those quantum bits can be in different states. For example, an atom that's excited or not excited, and can also be in superposition at different states, which is the wave behavior. Right? So you have the particle, which is which state you're in, and the wave behavior, which is superposition of the 2 different states. So the qubit is going to be in 0 and 1, and also in superpositions of 0 and 1s. And that's the whole heart of quantum mechanics. And I'm just going to show you how we're doing. So I'm going to do this like this, because that's actually the central slide of here. We're building a special laser. So that's a regular laser. A regular laser is based on a transition between two energy levels that emits photons one by one, okay? And when you do that, you put this photon emitting medium between two mirrors. One reflects everything, one transmits some of the light, so that the photons, once they're emitted, can actually come back and stimulate the emission of more photons. For all the frequencies that interfere, there's more interference here, interfere constructively after one round trip, and then comes out, the light comes out and photons are emitted very, very fast. And lasers are very powerful. Some lasers are extremely bright beams of light. They can travel far to the moon and back, but you have the light emitted photon by photon. Here, what we're doing is that we have a laser, again, it's the same thing as LIGO. It's a two-photon laser that emits photon 2 by 2. And all these peaks here are the different frequencies at which the light is emitted, the frequencies at which the light is constructively interfering after one round trip. We call them the resonance modes of the cavity, of the laser cavity. And those photons, photon pairs are emitted like that. And when they emitted like that, they create quantum correlations, we call entanglement, which we define, we can use to implement gates on the quantum computer. And because I took a lot of time telling you about wave particle, I'm not gonna, anyway, I wouldn't have been able, no matter what, to tell you in detail how the quantum gates come about. But we are, in fact, we've shown that we've been able in a single laser to actually create, using the wave and particle nature of this laser, and the fact that particles are emitted 2 by 2, which is absolutely fundamental. We've shown that we can create little quantum computing prototypes, and which looks like those guys here. So this is what the experiment looks like. So you have laser, laser, laser. Here we have our homemade laser that has those nonlinear crystals where the photon pairs are emitted, right? And we have this, it's a very complicated experiment. There's a lot of electronic controls to make everything stable. And then we verify the entanglement, which is the quantum correlations that are from the pairwise emission, and the fact that it's really giving us a quantum computing action, quantum gate action. And with we can also show that we can detect the photons. So we have signals from photons like that. You can see the photons. This is a 1 photon peak, 2 photon peak, 3 photon peak, like 5. And then we can go with detectors that tell us even more photons, and we can detect up to maybe 24 photons at a time. So we have different peaks. So the histograms, we have 0, 1, 2, 3, 4, 5, 6, 7. So we can do the photon detection and the wave detection. The wave detection is interference. We can see interference fringes. And like LIGO, like I showed you the bright and dark fringes on the cartoon. And we can also count the number of photons very, very precisely. And using that circuit, we want, our next goal is to make that tiny. Like, this is the first transistor at Bell Labs, 1947. It's very, very big chunk of, it's one transistor. In this chip, computer chip, we have billions of transistors, right? And this is a fingernail, not even. So we want to make quantum optical circuits where the photons are emitted. This is something we have in my lab. This is a little 2-photon laser. You have little mirrors there. This is a 4-inch high optical mount. This is all very macroscopic. And this is one of my collaborators at University of Virginia, Xu Yi, who's making those little lasers in microscopic. This is a penny, right? This is a little lithographic optical chip with lots of different optical parametric oscillators, 2-photon lasers. And Joe Campbell is making super sophisticated photodetectors that can see photons one by one. And Andreas Billing is putting them on chip also, so that we can build together an optical quantum computer out of photonic chips, and hopefully maybe replace those giant, this is the Summit exascale supercomputer at Oak Ridge, maybe make quantum computers that will be even able to beat, that's not going to happen tomorrow, but you know, with Robert Edward and Raoul, we're trying to understand this and see if we can make progress to compute very complicated things in particle physics using quantum computers. And I will leave you with that little sketch here, which is the inspiration for my whole career. I'm bragging a little bit. It's not completely true. Sometimes you have to do things that way, but you know, that guy doesn't know that this is food yet. Thank you for your patience.
That's a great place to end. Thank you so much, Olivier. If people have any questions, we can, okay, I see one question from Anonymous about whether we are certain about the wave nature of matter that we can observe experimentally whether it's not governed by some hidden variable.
That's a great question. Thank you for this question. So there is something that, and honestly, yeah, okay, this is just the way I organize things, but I can get, I'm so fascinated, honestly fascinated by the wave particle duality that I can just talk. This was for one system. Now for two systems,
maybe we should catch up to the non-experts about this hidden variable theory, right? So the idea is that
so quantum for mechanics, two systems, the two systems, the superposition can give you what's called entanglement. Raoul, if you want to.
No. You go ahead. It's your question.
Okay. So for example, you can have two particles. Take an example: two atoms that are excited, or two atoms that are not excited, right? But if you take a superposition of those two states, when the two atoms are excited, and it can be separated, they can be far away from each other. They're both excited and they're both non-excited. And it's a superposition because quantum mechanics allows superpositions. So what happens now? Well, if you measure one atom, you're going to find out if it's excited or not excited because you measure its energy and you're going to know what it is. But if it's not excited, then the other guy, because when you do a measurement in quantum mechanics, you do what we call a projection, a wave packet collapse. So that guy is going to be in the state it was when you measured it. And because the other guy is in the same state, just a superposition of both up, both down, then that guy is going to be down in that state too. And then, but you haven't done anything to that one. That's how do you know? And you can check, people can check. People have done that with photon pairs and sent like thousands of kilometers apart, and you measure one, boom, the other one is exactly in the same correlated state. So then Einstein said, well, how do we know that, you know, there isn't an extra theory and what Bell called a local hidden variable, what Einstein, Podolsky, and Rosen called the element of reality, that tells you what actually Einstein, Podolsky, and Rosen said there must be an element of reality. There should be, in any physical theory worthy of that name, there should be an element of reality that's local, that tells you what the measurement result is. And Niels Bohr said, no, it's what quantum mechanics does. That's, you know, just. And Schrödinger went even farther than that. He said, well, so then if we, you know, give any credit to that stuff, then there's a cat, it could be alive and it could be dead at the same time. And that's the beginning of entanglement. So hidden variables have been tested, though. They've been tested by Bell inequality violation experiments from a proposal of John Bell, who called them that, hidden variables. And we found that they don't, contrary to what Einstein postulated that they must exist, they don't have to exist. We haven't seen any, it's been infirmed, their existence has been contradicted every time, every experiment. If that answers the question, I hope.
I think so, yeah. I mean, I think I'll maybe add to that. I think quantum mechanics is just so fascinating. I mean, I've been working on it for, I don't know, at least 15 years and 10, 15 years, and it's still mind-boggling. So I'm sure that even basic questions like that are not so basic.
No, it doesn't get old. It's fantastic.
Yeah. So fortunately, we don't have any more time for questions. I have some more questions that I would ask you. So thank you so much, Olivier, for giving us a little bit of a glimpse into this world of quantum mechanics and quantum computing. We do have more questions, unfortunately. Yeah, well, people just saying,
if you want to email me, I'm easy to find. And you mentioned the REYES talk, and I make a solemn promise, I will reply to you. Please send me an email with your question. I'll be happy to do that.
Maybe what we need to do is, if you don't get tired of me, by next year, we invite you to come and give a follow-up talk on just quantum computing, because I think that is something that a lot of people will want to ask about. So,
yeah.
Okay, so well, with that, thank you so much, Olivier. It's been a real pleasure. Everybody, if you have any questions, feel free to search for him. Again, he's a professor at University of Virginia, so he's easy to find.
Pfister at virginia.edu. Yeah.
Yeah, and so please now join the other session, and don't forget, we have a tour of Jefferson Lab in an hour. So that's a really neat opportunity that you do not want to miss. Most people don't get to see a national lab.